From space, Earth's night side looks mostly dark, but not quite. Far from any city, small points of molten orange glow through the clouds, like quiet lanterns set into the crust. A crater lake with its surface just beginning to shine. A thin line of vents along a rift. A river of lava bending around an old ridge. Against the size of the planet, they are almost nothing, but each glow is a tiny window into the deep, slow engine inside our world. At my desk, those windows are just lines in a case file. I'm Madeline Rowe, astrophysicist turned field investigator. Tonight's folder is stamped in deep green ink, Volcanoes for sleep, conduits from deep Earth to the surface. In the shorthand notes I've just written, this is Volcanoes for sleep. It isn't a disaster briefing, it's a study of plumbing, of how heat and rock travel quietly upward, and of how you can drift off peacefully while we walk through it together. Before we wade into anything molten, give yourself a moment to get settled. Let your shoulders sag a little, like cooling lava relaxing into its final shape. Let your jaw loosen. Let your tongue rest softly so there's a little space between your teeth. If you are lying down, feel where the mattress supports you, from the back of your head all the way down to your heels. If you are sitting, feel the weight of your body passing through you into the chair, into the floor, into the bedrock, and down into layers of rock that have been there for hundreds of millions of years. You don't have to hold yourself up alone. The planet has you. Nothing in this file needs to be remembered. You are allowed to miss entire sections. You can doze in and out as your attention wanders. If you fall asleep halfway through a sentence about magma chemistry, that just means the case file is working. I will keep reading quietly all the way to the end, whether you hear it or not. The first page is a simple sketch of Earth in cross-section. Not the sharp, glossy textbook version, just a pencil drawing. A small, solid inner core in the center, surrounded by a shell of liquid metal. Above that, the mantle taking up most of the page, a thick layer of rock that moves so slowly it looks still. At the very top, an almost comically thin rind labelled crust. Volcanoes are tiny details near the top of this drawing. They are the places where the deeper parts of the planet talk to the surface. The mantle in the sketch looks solid, and in real life, it is. If you could somehow lift a piece of normal mantle rock up here to the surface, it would feel hard and strong in your hands. But at the depths where it usually lives, the pressure and temperature are so high that over long stretches of time, it can flow. Not like water, not even like syrup, more like cold honey that has all day to creep across a plate, or like a glacier inching down a valley. Heat from the planet's formation and from slow radioactive decay sets up enormous convection cells in this mantle. Hotter material rises, cooler material sinks. The whole shell turns over, but so slowly that a single full loop can take many tens of millions of years. On some diagrams in the file, those convection cells are drawn as broad, looping arrows. One arrow rises under a mid-ocean ridge. Another sinks beneath a subduction zone. Between them, arrows curve and bend, showing how material that was once deep in the mantle can eventually become part of the surface crust, and then later be carried back down. It is a very slow conveyor belt. Each loop is long, but always in motion. When mantle rock rises toward the surface, something subtle happens. The pressure around it drops because there is less rock overhead. The rock expands a little. Its temperature does not drop as quickly as the pressure does. There is a region in the pressure-temperature diagram where the rock is close to its melting point. As the pressure falls further, small fractions of the rock begin to melt. Not into a big underground lake, but into a sponge-like mixture of crystals and droplets of melt. This is decompression melting, one of the main ways magma is born. Along mid-ocean ridges where tectonic plates move apart, this process plays out constantly. The plates drift away from each other. Mantle material rises to fill the gap. As it rises, it crosses into that melting zone. Tiny droplets of basaltic magma appear between solid grains, merge, and start to move. Being slightly less dense, they percolate upward. Eventually, they reach the seafloor, where they erupt as pillow lavas and sheeted flows, building new ocean crust in quiet, steady pulses. Almost all of this happens in darkness, under kilometers of water. No one sees it directly, but it accounts for much of the volcanism on Earth. The file has a small sketch of a mid-ocean ridge as seen from the side. Two plates pull apart at the top. Below them, the mantle rises in a broad upwelling. Near the surface, a narrow zone of melt appears, feeding a knife-thin line of lava on the ocean floor. Around that line, hydrothermal vents dot the sea floor, where seawater that has seeped into the new crust returns, hot and mineral-rich. A note next to the drawing says that if you could hover there, you would see the ocean shimmering with heat above those vents, but feel nothing at the surface. There is another way to melt mantle rock, not by changing the pressure, but by changing the melting point. Picture an oceanic plate sliding downward into the mantle at a subduction zone. It carries water with it, locked inside minerals and sediments. As the plate descends and warms, those minerals release water into the overlying mantle wedge. Water lowers the melting temperature of rocks. Where enough water accumulates, patches of the mantle wedge begin to melt. The melt there often becomes enriched in silica and gases. It rises, pools, evolves, and over long intervals feeds arcs of volcanoes on the surface. In another diagram, the subduction system is sketched like a slow, deep waterfall. The plate bends and dives. A band of small earthquakes marks the path of its descent. Above that band, small red zones indicate regions of partial melting. Above those, a string of volcano symbols marks the volcanic arc. Between each symbol, arrows show that magma pathways can wander. Not every melt packet reaches the surface. Many will freeze in place as part of the crust. There are also narrower plumes of unusually hot mantle rising from deep within the planet. When the broad head of such a plume reaches the base of the lithosphere, vast volumes of basalt can form, pouring out as thick lava plateaus. After the head spreads out, the narrower tail can continue to rise. If a plate is moving overhead, the plume stays roughly in place while the plate drifts. The result is a track of volcanoes, like beads on a string, older and more eroded as you move away from the active hotspot. The Hawaiian chain is one example. Under the oceans, many more such tracks lie quiet, their volcanoes long since eroded and sunk. However magma forms, it eventually faces the same problem. It has to make its way through the crust. The crust is colder and more brittle than the mantle. It fractures and faults. Rising magma looks for these weaknesses. It forces its way into cracks, widening them slightly, freezing along the edges as it goes. Over time, these intrusions can form tall, sheet-like bodies of solidified rock called dikes. Some dikes reach the surface and feed eruptions, Many stop and cool quietly, never breaking through. When magma finds a level where its buoyancy is balanced by the weight of the rock around it, or where overlying layers are particularly weak, it may pool. Over long periods, such pools can grow into magma reservoirs. The word chamber suggests a big open cavern filled with liquid, but the reality is more complicated. These zones are mushy, full of crystals in partially molten rock, with melt moving around between solid grains. The proportion of melt can change with time. So can the chemistry. Inside these mush zones, crystals grow on walls and roofs, then settle or float depending on their density. Early formed minerals rich in iron and magnesium may sink, forming layers at the bottom. The remaining melt becomes richer in silica and volatile elements. New batches of hotter magma from below can intrude, mixing and reheating the system. Some parts crystallize, others remelt. It is less like a static tank and more like a pot of very thick stew that is being heated unevenly from below, with ingredients added and removed slowly over thousands of years. One of the pages in the file contains a small, detailed drawing of this mush zone. The pencil strokes are tight and controlled. Between them, I've shaded a path for one droplet of melt. In the drawing, that droplet starts deep in the mantle, where a bit of rock has just melted. It threads its way upward between solid grains, joining other droplets. Together, they form a small pocket. Over time, the pocket connects to others. They merge into a larger body that begins to rise, moving into the base of the crust. There, the melt pauses, spreading sideways, cooling at the edges, dissolving some of the surrounding rock and crystallizing new minerals. Our droplet gets mixed and remixed as fresh magma arrives from below. It spends centuries inside this partially molten sponge, sometimes on the hotter side, sometimes in slightly cooler fringe zones. Tiny changes in temperature and pressure shift which minerals are stable. Crystals grow and disappear. The droplet's composition slowly evolves. In the margin of that drawing, a note mentions that geophysicists infer these mush zones from seismic waves. Earthquakes send vibrations through the crust and mantle. Sensors record how quickly those waves travel through different regions. Where rock is hotter or partly molten, certain kinds of waves tend to slow down. By inverting many such measurements, scientists map fuzzy blobs of lower velocity rock, like blurred shadows of the mush zones we've been talking about. It is as if we can never see the droplet directly, but we can see the way it subtly changes how sound travels. Much later, a new pulse of hotter magma stirs the system again. The mush zone becomes a bit more liquid overall. Channels of melt connect. Pressure increases. Our droplet, now a different chemical mix than when it started, finds itself drawn upward along a new conduit. It rises into a shallower reservoir, then perhaps up into a narrow dike, and finally toward a vent on the surface. In one version of its future, it reaches the air, cools, and becomes a grain in an ash layer. In another, it is part of a slow, thick lava flow that moves downslope. In yet another, it cools underground, becoming a crystal in a pluton no one will see for millions of years. All of these futures are slow compared to a single breath. Speaking of breaths, you can take one slowly now. In through your nose, enough to feel your ribs gently expand. Out again, letting your shoulders relax. If details about crystals and mush zones are starting to blur at the edges, that is perfectly fine. You are allowed to let the exact processes drift away. The feeling of slow, patient movement is enough. From here, the case file moves from the hidden interior toward the visible shapes on the surface. One sketch shows a narrow conduit punching upward from a shallow reservoir to daylight, with a small cone built around it. The cone is made of loosely drawn pellets and shards. A note in the margin reads, "cinder cone." These forms often arise when basaltic magma rich in gas erupts in short bursts. Each burst throws glowing fragments into the air. They cool and solidify into scoria as they fall, piling around the vent. In a surprisingly short time, a few months or years, a cone a few hundred meters high can grow out of a field or hillside. Some cones erupt once and then never again. Others may be reused by later eruptions, reawakening briefly after long, quiet stretches. Another page shows a taller cone with alternating bands, labelled carefully. Broad, darker bands. Lava flow. Thin, lighter wedges, ash, pumice, pyroclastic deposits. This cross-section belongs to a stratovolcano, also called a composite volcano. Here, more viscous magma erupts in mixed styles. Some eruptions produce relatively short, thick flows that cool into steep-sided lava tongues. Others fragment the magma into ash and pumice that settle out in layers. Over thousands of years, these alternating deposits build a high, steep mountain. Many famous volcanoes with symmetrical snow-capped silhouettes belong to this class. On the next sheet, a giant low-slung shield spreads outward. The slopes are gentle, drawn almost flat, but the vertical scale reveals their thickness. Thin, fluid basaltic lava has flowed from vents near the summit and from rifts along the flanks. Each flow travels long distances before freezing. Over time, hundreds of overlapping lobes build up a shield volcano. From the ground, walking on such a volcano can feel like strolling across rolling hills. From the side in cross-section, you see that you are actually traversing thick stacks of basaltic sheets. Lava domes occupy one corner of the file in a set of small frames. The first image shows an opening vent. The next shows a plug of magma that has barely moved, just bulged upward. In later frames, the plug has grown into a steep, blocky mound, cracked and layered. Here, the magma is so viscous that it does not run. It oozes upward and piles on itself. The outer skin cools and fractures while the interior is still warm. Domes can grow slowly over months or years. Sometimes they become unstable and collapse, feeding pyroclastic flows. Sometimes they simply sit, a stiff cap changing only very gradually. Not all volcanism focuses on single points. Long fissures can open along rifts and volcano flanks. When basaltic magma rises along these fractures, it can erupt as curtains of lava fountains. The fountains build walls of spatter. Lava drains downslope in broad sheets. In the distant geological past, enormous fissure eruptions have poured out enough basalt to cover regions the size of countries or small continents. We meet those in old rock records as thick, stacked plateaus called large igneous provinces. Once the shapes have been described, the case file turns gently to behaviour. One section collects eruption styles, like entries in a quiet catalogue: Hawaiian, Strombolian, Vulcanian, Plinian, Plinian, steam-driven events where external water is involved. The differences between them trace back to the viscosity of the magma, its gas content, and the presence or absence of water around the vent. Hawaiian-style eruptions are among the most gentle for observers who keep a safe distance. Fluid basaltic lava emerges steadily from vents or fissures. Lava fountains arc upward and fall back on themselves, feeding flowing rivers of melt. These flows move downhill, filling low spots, crawling around obstacles, sometimes forming lava tubes that insulate the molten interior so it can travel kilometers. For people living nearby, the main concern is not surprise, but where the flows will go and what they will cover. Scientists map topography, monitor flow rates, and help authorities decide which areas to close or evacuate long before the lava arrives. Strombolian activity looks as if the volcano is breathing. Gas slugs rise through a column of magma and burst at the surface. Each burst tosses glowing clots of lava into the air. They follow graceful arcs and land, cooling into scoria. The interval between bursts might be a few minutes or longer. Observers watching from official lookouts see one burst, then calm, then another. Over months, these bursts can build or rebuild cinder cones. Volcanian eruptions involve short, explosive bursts, where a stiff plug of magma at the top of a conduit is broken apart. Ash and blocks are hurled into the air. The resulting clouds may be dense but short-lived. Such eruptions can be part of a sequence that gradually opens the conduit, or they may simply be the system venting pressure. Monitoring networks pay close attention to their patterns to distinguish between those possibilities. Plinian eruptions create the tall columns so often drawn in older diagrams. Gas-rich, viscous magma fragments violently as it erupts. The mixture of hot gas and particles rises rapidly, forming a pillar that can reach the stratosphere. At some level, the column spreads outward, forming an umbrella-like top. Ash then drifts downwind, carried by high-altitude winds. Far from the vent, the deposit might be no thicker than a sheet of paper, but its chemical fingerprint can still identify its source centuries or millennia later. When external water is involved, the style changes again. If groundwater, lake water, or seawater encounters hot rock or magma, it can convert rapidly to steam. The expanding steam fragments surrounding material, these phreatic or phreatomagmatic eruptions, can blast out older rock with little or no fresh magma. Because they depend on subsurface water pathways, they may not show the same gas or deformation warning signs as magma-driven eruptions, so geothermal areas and crater lakes are treated with particular respect. Eruption styles produce different products, and those products bring different kinds of hazards. The file continues, but the tone stays steady and matter-of-fact. Lava flows, for instance, look dramatic when glowing red at night, but their motion is usually measured in meters per hour, or even slower, especially on gentle slopes. Given reliable mapping and warning, people step aside. Roads may be overrun, fields may be buried, houses may be lost. Yet after the eruption, the new rock gradually cools, cracks, and weathers. Within a human lifetime, plants begin to take hold. Within several lifetimes, what was once a glowing river becomes a green hillside, with only hints of dark rock showing through. Pyroclastic density currents are more dangerous near the volcano. These fast, ground-hugging mixtures of hot gas and particles surge downslope under their own weight. They can form when eruption columns collapse, when lava domes fail, or when parts of a cone give way. In deposits, they appear as layers of ash and larger fragments welded or compacted together, sometimes with cross-bedding that tells of turbulent flow. Geologists map these deposits to learn how far past flows have travelled. Those maps help define exclusion zones where people do not build, or where evacuation plans must be especially clear. Volcanic ash connects volcanoes to regions far away. Fine ash carried by the wind can travel across oceans and between continents. The case file shows satellite images of ash plumes traced across the atmosphere. Airlines work with volcanic ash advisory centres to reroute flights when such plumes are present, because these tiny, hard particles are not kind to jet engines. At ground level, thin ash layers can make roads slick and air gritty. People may wear masks and goggles for a few days. Municipal workers clear ash from roofs and gutters. Afterwards, the ash becomes part of the soil. Lahars, mixtures of volcanic debris and water, have their own section. Heavy rain on fresh ash deposits, sudden melting of snow and ice during an eruption, or the failure of a crater lake can trigger these dense flows. They follow river valleys like wet concrete, carrying boulders and logs. Old lahar deposits form broad, flat plains downstream of volcanoes. Those plains are often fertile and convenient for settlement. So many towns lie on top of older lahar fans. Modern hazard maps overlay lahar pathways, and communities run practice drills so that if new flows are ever generated, people know which way to go and how much time they are likely to have. Volcanic gases are another part of the story. Water vapour is the most abundant. Carbon dioxide comes next, then sulfur dioxide, hydrogen sulfide, and a host of minor gases. Near vents, concentrated gases can accumulate in low spots on calm days, or irritate eyes and lungs. In some valleys, invisible carbon dioxide can build up enough to displace normal air near the ground. At the same time, these gases are powerful diagnostic tools. Networks of gas sensors measure flux and composition. Changes in the relative amounts of carbon dioxide and sulfur species can signal new magma rising or changes in the hydrothermal system. Satellites detect sulfur dioxide from space, providing a broader view. As you listen to all of this, you might feel like the file is getting dense. If you notice details slipping away, that is more than acceptable. You are not in a class. You are not being tested. Think of the information like ash settling through the air. Some of it will come gently to rest and stay. Some of it will stay suspended and drift away with the breeze of your thoughts. The point is not to carry a neat summary into the morning. The point is that your body gets a chance to rest while your mind wanders through slow geology. The file now shifts from processes to people. There is a section describing a volcano observatory in more detail. We were there briefly at the beginning. Now we walk more slowly through its rooms. In the main control room, seismometer traces scroll across multiple monitors. Each instrument sits out in the field, some mounted in vaults near the volcano, some farther away. When a tiny earthquake occurs, a small wiggle appears on each trace in turn. By comparing arrival times of those waves, scientists can locate the source, like using the difference in a thunderclap's arrival to guess how far away the storm is. The plotting software marks each detected event with a dot on a map, tiny specks blooming and fading around the volcano. Some nights, there are almost none. Other nights, a whole cloud of microquakes comes and goes as fluids shift deep below. On another desk, computers track data from GPS receivers installed on the volcano's flanks. Each receiver listens to satellites and reports its position to within millimeters. The positions drift slightly as tectonic plates move, as seasonal snow loads come and go, and as magma moves. Over days, a station might creep outward, then pause, then subside. Plotted on a screen, the motions are barely noticeable unless you zoom in. When viewed as arrows on a map, they show the volcano breathing over months and years. A separate monitor shows satellite-based radar data. Interferograms, colourful fringe patterns reveal changes in the shape of the ground between satellite passes. Concentric rings of colour around a crater can indicate uplift or subsidence of only a few centimetres. In the file, one such image is clipped and taped to a page, with arrows noting where the uplift suggests magma is accumulating at depth. In a corner of the room, shelves hold gas sampling gear, lightweight backpacks with tubing, small evacuated flasks ready to be filled near fumaroles, portable instruments that measure carbon dioxide and sulfur dioxide in real time. Nearby sits a thermal camera capable of mapping surface temperatures, used to scan crater lakes and lava flow fronts from a safe distance. There are hard hats, headlamps, and protective masks hanging on hooks by the door, waiting for the next field trip. One page in the file describes a typical day in the field for a small team. In the early morning, before the air heats up, they load equipment into a sturdy vehicle. Seismometers wrapped in padding, tripods for GPS antennas, gas analyzers in their cases. They drive up a narrow road that winds along the flank, trees giving way to more open slopes. Dust rises in the vehicle's wake, then settles behind them. At the first stop, they install a new seismometer. They dig a shallow pit in firm ground, place the sensor on a concrete pad, and carefully orient it. Cables run to a weatherproof box holding the data logger and power system. A small solar panel tilts towards the sky. Once the lid is closed, the instrument quietly begins to listen, sensitive to vibrations too small for human senses. Later in the day, the team climbs on foot toward a steaming fumarole field. They move slowly, not because the slope is too steep, but because gas concentrations vary with every shift of the wind. Masks hang around their necks, ready if needed. At each fumarole, they briefly dip a tube into the vent, filling a small flask. Temperatures are measured. Notes are taken about the smell, the sound, the colour of deposits around the opening. Then they step back, letting fresh air wash around them before moving on. In the afternoon, back at the observatory, they download data from the GPS stations they visited earlier. The new points extend lines on graphs that have been growing for years. Slight trends become clearer. Uplift here, subsidence there. They compare the new patterns with older episodes of unrest, looking for similarities and differences. Downstairs, in a quiet instrument vault, a broadband seismometer rests on a concrete pier. Cables snake away to the control room. The sensor is sensitive enough to pick up not just local quakes, but distant waves from large earthquakes on the other side of the planet, and even microseisms from ocean waves hitting shorelines. The instrument room smells faintly of dust and cool stone. The air is still. In that stillness, the sensor detects every tiny vibration. All of this infrastructure exists for one main purpose: to give as much early warning as possible if a volcano's state begins to change in ways that could matter for people nearby. Not every increase in activity leads to an eruption, but every change is noted, graphed, and compared with past records. This slow, steady watchfulness is one of the reasons you can relax while we talk about volcanoes in the abstract tonight. Before the file leaves the observatory, it pauses once more in the control room at night. Most of the building is dark. Only a few small desk lamps are on. A technician or a scientist on duty sips something warm and watches a bank of screens. Seismic traces move, Gas readings update. GPS plots refresh. Outside, wind moves through trees. Snow, if there is any, softens sound. The volcano itself is just a dark shape against the stars. You can let your breathing sync up with that quiet scene for a few moments. In and out. No rush, no urgency. Just a steady, gentle rhythm. The kind instruments would show as nearly flat lines. The case file then widens its scope again, stepping back from individual instruments to look at the wider role of volcanism. Over long spans of time, volcanoes participate in Earth's climate system. Large explosive eruptions that inject sulfur dioxide into the stratosphere can create sulfate aerosols high above the clouds. These tiny particles reflect some sunlight. For a year or two after such an eruption, global average temperatures may dip slightly. Sunsets can look deeper and richer as light scatters through the high haze. Eventually, the particles settle out, and the atmosphere returns to normal. A diagram in the file shows the atmosphere as stacked layers. Near the surface, the troposphere, where weather happens. Above that, the stratosphere, more stable and layered. Ash and gases from modest eruptions may stay within the lower layer, affecting regional weather for days or weeks. Very powerful eruptions can loft sulfur-rich gases into the stratosphere, where they spread around the globe and influence climate for a year or two. The drawing shows arrows carrying tiny dots of aerosol around the planet, then drifting gradually downward. Carbon dioxide from volcanoes enters the atmosphere as well. On human timescales, the flux is small compared to modern industrial emissions, but on geological timescales, it contributes to the background level of greenhouse gases. Weathering of volcanic rocks on land consumes carbon dioxide, transforming it into dissolved ions that eventually become carbonate minerals in the oceans. The balance between volcanic input and weathering output helps set Earth's long-term thermostat. The cycle is slow, measured in millions of years. It simply continues in the background while everyday weather comes and goes above. One page draws this as a balance. On one side, a sketch of volcanoes releases carbon dioxide. On the other side, mountains under rain are labelled weathering. Arrows connect minerals in rocks to ions in rivers and then to sediments on the seafloor. Under those sediments, a small note says that some of this material will one day be subducted, releasing carbon dioxide again far in the future. The whole loop is an immensely long, gentle breathing of carbon through the solid Earth and its thin atmosphere. From here, the file takes a quiet detour into planetary volcanism beyond Earth. On Mars, enormous shield volcanoes dominate parts of the surface. Olympus Mons rises about 22 kilometers above the surrounding plains, its base sprawling for hundreds of kilometers. Low gravity and a lack of plate motion, they're allowed repeated eruptions from nearly the same spot. The slopes are gentle, like an immense frozen wave. Standing near its flank, in your mind, safely and comfortably, you would see a horizon that curves upward almost imperceptibly. The sky would be thin and pink. The rocks beneath your feet would be basaltic, cousins to those on many lava flows on Earth. The file includes a small series of sketches of Mars. One shows ancient valley networks cut by water long ago, with volcanic plains in the background. Another shows a cross-section of a shield volcano, similar in shape to some on Earth, but scaled up. There is a note that Martian volcanoes may now be dormant or extinct, their heat output much lower than in their prime. Still, frozen in their shapes is a record of a more active interior. On Venus, the surface is hidden beneath a thick, hot atmosphere. Radar imaging has revealed broad volcanic rises, dome-like structures, and complex flows. Some of these features likely represent ancient or relatively recent volcanism. Without clear views or long-time series data, it is harder to say exactly how active Venus is today. Still, the patterns of its plains suggest that lava has flowed there over large areas. In the case file, Venus appears as a radar contour map pinned next to Earth cross-sections, a reminder that volcanism is a common planetary language. The Moon preserves another kind of volcanic story. Dark Luna Maria, the seas seen from Earth, are basaltic plains formed by ancient lava flows that filled large impact basins. Those flows are long cooled now. No volcanic gases rise from them, but astronauts who walked on their surfaces brought back samples that show many of the same minerals found in terrestrial basalts. In that way, even a silent world can tell a volcanic tale. Around Jupiter, the small moon Io orbits in a zone of intense gravitational tug-of-war. Tidal forces flex its interior, generating heat. Io is, as far as we know, the most volcanically active body in the solar system. Observations show towering plumes of material arcing hundreds of kilometers into space. In the file, there is a small artist's impression, Io's mottled surface with bright plume umbrellas against the black. It is a visually striking scene, but also extremely distant from the quiet of your room. Farther out, icy moons such as Enceladus and Triton show signs of cryovolcanism. Instead of lava made of silicate rock, these worlds may vent mixtures of water, ammonia, and other ices. Plumes of vapor and fine ice grains jet from cracks, especially near Enceladus's south pole. The Cassini spacecraft flew through those plumes and detected salts and organic molecules. In that sense, these icy volcanoes are cousins to hydrothermal vents on Earth's seafloor. They hint that even in places far from the sun, internal heat can drive circulation of liquid and provide energy sources for life. The file briefly mentions worlds beyond our solar system. Super-Earths close to their stars may have vigorous interiors. Some exoplanets are thought to be covered in magma oceans or dotted with lava lakes on their day sides. We only see them as faint dips in starlight, but models suggest that volcanism there could be intense. It is a reminder that the process of bringing interior heat to the surface is not special to one planet. After this tour, the file gently closes the section about other worlds. For tonight, it says, "We are back on Earth, the only planet we know where volcanoes, oceans, air, and living things all interact to create comfortable beds, quiet neighborhoods, and desks where case files can be opened." At this point in the recording, you might like another small pause for yourself. Feel where your hands are resting. Notice the weight of your arms. If your thoughts have wandered to unrelated topics, that's fine. Let them drift back briefly and then soften again. Just as magma can sit quietly in a reservoir for a long time without doing anything dramatic, your mind is allowed to rest without producing anything. No problem needs solving right now. The file turns toward archives and memory. We already visited one kind of archive, where cores of lake sediments record ash layers as thin stripes. Another room in another building holds long cylinders of ice. Ice cores are stored in cold rooms, stacked on shelves. Each core is a history of snowfall, compacted and preserved. Thin, dusty layers in the ice can mark years when volcanic ash or sulfate aerosols settled from the sky. Chemists slice segments of the cores carefully, melt them, and analyze their composition. Spikes in sulfate concentration line up with known eruptions. Others reveal events that left little written record but affected the atmosphere nonetheless. Tree rings add their own perspective. In some regions, rings from long-lived trees show years of slower growth that coincide with cooler summers following major eruptions. Combined with ice cores, sediment records, and written observations, they help scientists reconstruct how often big eruptions happen and how far their effects reach. None of this is meant to unsettle anyone listening in the present. It is simply part of the planet's long diary, written in layers of ice, mud, and wood. There is also a quieter kind of archive in the observatories themselves. In filing cabinets and digital drives, decades of monitoring data are stored. Seismic records, gas measurements, deformation time series, photographs from repeat surveys. Each entry by itself is ordinary. Together, they show how individual volcanoes live most of their lives, in small fluctuations around a calm baseline. Some of the last pages in the file hold personal field notes, sketches of lava textures, lists of dates and weather conditions, descriptions of the way a crater lake's colour changed over one summer, notes about how communities in nearby towns responded to drills with a mix of seriousness and humour. These human details sit alongside the technical data, giving a fuller picture of what it means to live with volcanoes. By now, the case file has grown thick. The early pages about mantle convection and decompression melting sit under later pages about eruption styles, hazards, monitoring, archives, and other worlds. If you leaf through it, a fine dusting of pencil shavings would probably fall out onto the desk. For you, the details can blur together in a gentler way. Perhaps the image that sticks is a single one. A quiet observatory at night, a slow lava flow in fading light, a rack of ice cores, or a dim drawing of Earth in cross-section. Any of those is enough. You do not need to hold the whole structure in your head. You only need to sleep. The closing pages of the file return to where we started. You, gravity, and a planet with a warm interior and a cool surface. Under whichever place you happen to be listening from, there is crust. Beneath that, mantle. Somewhere deeper still, in patches and streaks, are zones of partially molten rock. They will continue to form and reshape slowly, whether or not anyone thinks about them. While you breathe, millions of small processes are underway that you never have to manage. Tectonic plates glide a few centimeters each year. Mountains rise and erode. Old ocean crust is tucked back into the mantle and recycled. New crust is added at mid-ocean ridges. All of it takes place on timescales so long that a single night's sleep does not register. In contrast, your body responds quickly to rest. When your eyes close, muscles loosen, heart rate slows, nerve cells adjust their rhythms. Sleep stages cycle and recur. While all of that unfolds, the case file on volcanoes can simply sit on this imaginary desk, papers settling under their own weight, a cup of tea cooling beside them. Before the very end, the file takes you through one more gentle circuit of its favourite scenes. First, the observatory at night again, screens glowing softly, a low hum of equipment. Outside, the dark outline of the volcano under a scattering of stars. Instruments listen for movements within the mountain. Most of what they record is background noise, wind, distant storms, tiny tectonic adjustments. That quiet baseline is what allows scientists to notice when something changes. Tonight, in this story, the traces stay calm. Nothing urgent happens. The person on duty notes this in the logbook and lets the building fall silent around them. Then, the walk across an old lava flow at dusk. The rock underfoot is firm, with a rough, knobbly texture. In some places, it is ropey and smooth, with frozen ripples where lava once folded on itself. In others, it is jagged and broken, like a jumble of clinker. Small plants cling to cracks, their roots reaching into pockets of soil forming from ground-up rock. The air cools as the sun lowers. The lava, which once glowed, now simply holds onto the last warmth of the day. In the distance, a larger volcanic cone stands quietly, smoke-free, snow-patched, watching over thinner cones and hills around it. Next, the archive of cores and ash. In a cool room, long cylinders of ice and sediment rest in racks. Each carries a label with numbers and codes. A scientist in a warm jacket lifts one core onto a lit table. They trace layers with a gloved finger. Here, a band marking a known eruption. There, a faint layer whose source is still uncertain. Samples are taken, analysed, logged. Outside that room, the world goes on as usual. Inside, patient work converts layers into timelines, and somewhere deep beneath the ocean surface, a small, remotely operated vehicle hovers near a submarine volcanic cone. Its lights pick out rounded pillow lavas and shimmering water above a hydrothermal vent. Tube worms and clams cluster where hot, chemical-rich fluids meet cold seawater. The volcano there is not erupting today. It is simply leaking heat and minerals at a steady rate, part of the long, slow exchange between interior and ocean. On a ship far above, people watch the video feed in a dim control room, speaking quietly so as not to disturb concentration, even though the vehicle cannot hear them. All of these scenes are connected by one thing: a planet that moves heat from inside to outside in many different ways, on many different timescales. Volcanoes are one expression of that movement. They can be dramatic when they are active. They can be quietly generative when they rest, building soils and landscapes. They occupy only a thin skin on a deep world. Tonight, you do not have to track any of this in detail. You can let the scenes fade into each other: the observatory, the lava flow, the archive, the submarine cone. Each one can drift away like a plume thinning in the upper air. This is Volcanoes for sleep, a quiet record of hot interiors, slow flows, and careful watching. It will still be here in the morning if you ever want to listen again. Nothing in it expires when you fall asleep. As we come to the end, you can let your attention shrink down to just a few things. The contact between your body and whatever supports it. The gentle movement of your breathing. The way your eyelids feel. If they are already heavy, you can let them stay closed. If stray thoughts try to flare up like little eruptions, you can let them do what many small bursts do in real volcanoes: rise, release their energy, and then die away without changing the overall shape of the mountain. Picture, just for a moment, a volcano after a long sequence of events. The lava has cooled. Ash has settled. Monitoring instruments still run, but most nights their lines are flat. Grass begins to return to the flanks. In the towns below, people light evening lamps and then turn them off again. Bedrooms are dark. The volcano is not off. It is simply resting, storing heat deep within, part of a slow cycle that will continue far beyond one human lifetime. Tonight, you get to copy that pattern on a much shorter scale. Any activity from the day can stay in its own part of your mind, like magma kept safely deep in the crust. At the surface of your awareness, there can be only cool, quiet darkness, a calm cone under a starry sky. I will close the file now in this little mental office. The folder slides back into place among the others. The lamp over the desk clicks off. Footsteps recede down a hallway. A door closes softly. Nothing more is required from you. Let yourself settle. Let your breathing find its slowest, easiest pattern. Let the weight of the day sink out of your muscles and into the bed beneath you, as gently as ash settling onto a still lake. Good night. Sleep well.